Oh, all right, good afternoon. Here we are yet again for another lovely session of ENGR 2302 Engineering Dynamics. In fact, this is going to be our last section of ENGR 2302 Engineering Dynamics. This is the last lecture of the semester. Yeah, tear. At least I didn't get an applause, so anyway. I don't know. I didn't know what I was expecting. I don't know if I was going to get... Okay. So let's begin. Today we're going to just introduce the topic of vibrations. This is one of the topics of the course. It is nice to know, but it's one of the more difficult topics to convey. So I just like to, and something that's seen more in later classes. So I like to just introduce you to some of the basic principles. We're going to be discussing this at a more qualitative level than anything, but I do want you to be aware of the topics of mechanical vibrations. So, topic du jour is mechanical vibration. Mechanical vibration. Mechanical vibration, okay. And this is important in many settings, many applications. And the ideas of some of the applications of mechanical vibration. Well, obviously we're dealing with masses and objects moving in some sort of rhythmic fashion. And let's look at an example of this. Sort of rhythmic fashion. And why is it important to engineers? So really what I want you to be familiar with today is I want you to be familiar with some of the basic topics and some of the why we are concerned about them as engineers. Rhythmic motion or periodic motion, and we'll define this more specifically. But at a more basic level, I want to talk about why this might be bad. Why might vibration be bad, or what are some instances of vibration? So, an example that I can think of in, say, I'll give you an example for both mechanical and civil engineering. An example in civil engineering, for those of you with the good sense to enroll in civil engineering. Anyway, that's mean, sorry. Anyway, for those interested in civil engineering, an example of vibration in a civil engineering application would be something like a building in an earthquake. So in an earthquake, when the ground moves, the building will respond with a certain. We'll have to respond to this vibration. Now the ground is going to vibrate back and forth with a certain frequency, and depending on the natural frequency of the building, which is something you may have heard about in other courses or something you may have heard about in physics class, and something we'll talk about here if we have time. And it is a property of the structure, the property of the building. How fast, if you just say, in other words, if you pull this thing back and release it, what would be the period of the vibration? And if that vibration matches up with the period of vibration of the ground, you can get just like say a child on a swing, their amplitude builds up more and more and more because the period of the pushing matches up with the natural period of the swing. You get motion that builds and builds and builds, and that is where you can get such things like structural collapses in buildings under earthquake load. That's where you get really dangerous vibrational loading. Or we could also pull up the example of the Tacoma Narrows Bridge, which I might do if we have the time. So structural vibration or structural dynamics is a case where vibration is important in civil engineering. Now, another example in mechanical engineering would be something that comes to mind for me is an engine or a rotating piece, whether it be a turbine, a shaft, or whatever it is. So imagine a turbine with propeller blades, with a series of turbine blades, and I'm going to draw some very poorly rendered turbine blades. That's a really wonky turbine. And this thing's going to rotate. Looks like it's made of balloons. Please don't make your turbines out of balloons. Anyway, so this thing is going to rotate. Now, you would actually construct this to much greater accuracy or precision than my crude drawing here. And to the eye, it would look like it's perfectly symmetrical. But is that possible? Of course not. You can never construct something perfectly symmetrical unless you have, magic atomic scale precision or something like that, which of course just isn't possible. There's always going to be one of these propellers, one of the blades on your turbine or a wheel or whatever it is, or if it's a rotating shaft, like a drive shaft, You might try to make it perfectly circular. You might try to give it a perfectly circular cross section, but so you might try to design it like this, perfectly circular, but in reality it ends up kind of like this. It's always going to be a little bit ellipsoid, isn't it? You're never going to get exactly perfectly circular, no matter how exact your instruments are. Now, if you want to, you might spend a lot of money and you might make it circular to within 1,000th or a 10,000th of an inch, but it's still not exactly symmetrical. You can never get something perfectly symmetric, perfectly circular.
This is the idea behind balancing a tire?
It's the same idea as balancing a tire, yes. And that's one way you can deal with the vibrational issue. See, one of the issues with this is so the problem with this is what's wrong with it not being perfectly circular? Well, if you think about it, if you have compare a tire to just something like a single rod weight on a rod. So you have a weight, a rotation point, and a rod. What's going to happen to this is this thing's going to go around and around and around, and it makes sense that this central point is going to experience forces on it that are up and down and up and down and up and down, or side to side, depending on your perspective, right? It's going to experience a continuous vibrational force, the support will. Does that make sense? You're going to have a certain vibrational force applied to this thing. So in other words, in order to we've mainly looked at centripetal force as a one-way force, but like all forces, it's a two-way force. So there's going to be a centripetal force necessary to make this thing go in a circle, but when this thing is flying around and this mass is being pulled downward, the central point is being pulled upward. And so that means the axis is going to be vibrating up and down or to the side or something like that. It's going to be oscillating as the weight goes around. Now, that's the extreme case, but every single case of an unbalanced system, there's going to be some degree of this kind of back and forth vibration. So you might try to create a perfectly balanced wheel, but inevitably there's going to be some level of vibration, and vibration means stress. And if your vibration is too large, if the vibrational forces are too large, they will tear your machine apart. Now, of course, there are some cases where you actually want vibrational forces. Things like things that come to mind in civil engineering are things like a shake table. Sometimes you use shakers, which are things used to if you've ever taken a soil design or a concrete design class, or a materials class, you may see things like shaker tables that you use to sort aggregate. They have a series of sieves, and imagine a series of trays of different sized holes, and you just have a big weight that shakes back and forth, a big motor, and just shakes back and forth. Also, there are concrete vibrators, which are just these large objects that you embed into wet concrete to mix it and make it go through all the molding and things like that. So, and usually all those vibration systems use some sort of they deliberately take advantage of that. So they have a rotating shaft, and then they have off-axis weights, and so they're designed to deliberately produce large amounts of vibration. So there are a few cases where you actually want vibration. Now, although in most cases of civil and mechanical engineering, vibration is not desired, but there may be some cases where it is desired. But they are going to be the exception rather than the rule.
I got a question for designing columns and all that, for a place that's prone to have earthquakes and stuff. Would the factor of safety be different than a place that doesn't ever have that kind of thing?
The question is, if you are in a place that has earthquakes in civil engineering,
That's kind of a different topic.
No, it's fine. Will the factor of safety be larger? Because of that, I wouldn't say the factor of safety would be larger. It's probably the same kind of factor of safety, but you'll learn when you get to your higher level coursework that we calculate different types of loading separately and apply different load cases. So seismic load is its own load case. So that's taken into account in the design of that particular load case. Yes.
I think there's different occurrences happen from different places, right? We don't really get earthquakes here.
Exactly, yes, and everything's localized. For example, in Houston, you're not going to be designing buildings for much snow load. In Denver, you're not going to be designing buildings for much hurricane load. It's just that would be also you're not. You have different load. So, in civil engineering, the way it works is you in terms of structural design, you calculate first. You calculate loads. You calculate the maximum expected earthquake load, maximum expected seismic or maximum expected wind load, rain load, snow load, dead load, live load, all of these things. And then you have sort of what things are called load cases, which are the sort of probabilistic models that take into account when different things are likely to occur. So the dead load is always going to be there. That's just the weight of the structure. So all the load cases have at least one for the dead load, usually 1.2. And however, though, in other words, it's based on probability. So yes, your building needs to be able to withstand the maximum wind load and the maximum rain load and everything else, and the live load. Like the live load would be like for a building like this, like a school building. Like let's say we had some big event in here, and there's only actually most of the time there's nobody in here because most of the time this building is empty at night or whatever. But the maximum case of live load for a classroom like this would be like, I don't know, let's say for some reason a student group had a event and we moved all the tables out of here and there was a really popular speaker that came by and there were 200 people in this room. I don't know if that would pass fire code, probably wouldn't, but we'll ignore fire code and have 300 people here or something like that. We could physically cram 300 people shoulder to shoulder in here, but that would be about the limit of the crazy live load that we might experience. So that's kind of the limit for live load for this room. But what are the chances that we're going to have that crazy peak live load at the same time we have the hurricane? Is that really going to happen? Or even during a hurricane, when you have different peak rain and wind loads, is the chance of having the peak wind load be like maximum peak gust? That's an instant, and the peak rain load be the point where there's the most rain hitting the building at a particular instant. Those are not going to happen at the same instant in time. Same thing with in areas that you do. Now there are some areas where you are unfortunate enough to have to design for both seismic and hurricane loading. We don't have to deal with much earthquake in Houston, but some areas like Puerto Rico, they have to worry about hurricane and seismic load. So that gets really hairy there. But they don't have to design them for both at the same time. Because what are the odds that a hurricane is going to strike the same time the big earthquake hits? That's just where you just need to start, consulting a priest or something, because you made somebody mad. I don't know. Anyway, you've pissed somebody off. But anyway, we structural engineers can't help with that. So anyway, but all of them have that kind of thing as well. They're all based off of probabilistic models of what are the chances of both of these things happening at the same time, all that kind of thing. So does that kind of answer that question? That was a bit of a tangent. Anyway. Okay, so let's discuss first vibrational terminology. Vibrational terminology. Or actually, I want more alliteration. Vibrational vocabulary.
It's too late in the semester.
I could say vociferous vibrational vocabulary. Vociferous, does that even apply here? Maybe, maybe not. Okay. Vibrational vocabulary. Okay. So the first thing to keep in mind, these terms you may have heard before, so I know this may be repetition, but I just have a few things I want to define. First, the period. What is the period of vibration? Someone said the period of the time of one revolution. That could definitely be the period, but I want to define it in more general terms. It is the time to complete one cycle. So any kind of rotary system, yes, it's going to be the time. It's going to be a rotation or revolution. But we could also have something like a spring on a weight that's just a weight on a spring that's just bouncing back and forth. And so the period is the time to complete one cycle. And vibration can be very generic. We can talk about a pendulum going back and forth. We can talk about a spring vibrating up and down. We can talk about a building flexing back and forth in the wind, or a motor rotating with an off-center weight. We can define it in many different ways. But anyway, the period is the time to complete one cycle. Then, of course, we have the frequency. What is the frequency? What is the frequency? Yes, it's the reciprocal of the period. It is the 1 over the period.
We're always so close, but not quite there.
Or the number of cycles per second. Yes, inverse and reciprocal are very close, but just not quite there. It's the number of cycles per second, and we measure this in hertz. So if you have a radio signal that is at 100 megahertz, the the radio waves are vibrating back and forth 100 million times per second. Quite fast. I wouldn't want to do that by hand. Then, what is the amplitude? What is the amplitude of a system? Of a vibrational system?
The maximum.
It is the maximum displacement, yes, from equilibrium position. Max displacement from the equilibrium position.
That should be on the test, like just the vocabulary.
There may be.
Worse than
It's like matching. 1, 2, 3, and then A, B, C.
You're quick to grade.
what grade do you want?
Just from the baseline to the peak of the. From the baseline to peak and then to a trough.
Yes, exactly. We'll look at some graphs of those, yes. Position. Let's see. Okay.
Right.
And then we also need to discuss two things. I'll do this on the next page because I want to distinguish between types of vibration. Okay. So types of vibration then. Types of vibration. So these are some basic terms that we need to be aware of before we start exploring these. And some types of vibration, well, we have both free vibration and fixed vibration. So we have two ways of classifying them. So I'm going to group these into two categories. One set of categories here, another one here. So the first thing I want to distinguish is free versus forced. Versus forced vibration. And damped and undamped. Damped vibration and undamped vibration. Oh, derp. Damped, undamped. Damped vibration. And undamped vibration. Okay, so what is free vibration? What do you think that means? It's free to vibrate. Thank you. Free vibration simply means an object vibrating or a system vibrating without, yes, by itself. By itself. Very simple. Of course, people ask, are they going to get extra credit for answering a simple and question? Anyway, forced vibration is, so in other words, an example of this would be if I just have a spring, I pull it back and watch it bounce up and down or back and forth or whatnot. Even if I could go to the, any kind of object that's vibrating back and forth. A pendulum would be in free vibration generally, anything like that. Forced vibration is a periodic force is applied to keep the object moving or to keep the object moving.
Like a child in a swing set with a parent pushing them.
Exactly. That would be an example of a periodic vibration, a forced vibration. So let me just write this down first. A periodic force is applied. So an example of forced vibration, yes, would be like a parent pushing the child on the swing, or even the child pumping leaning back and forth to pump the swing themselves. That would be force as well, because it would be free if they just sort of like locked into position and just sort of became a pendulum and just let themselves slow down gradually or something like that. That's free vibration. But, huh?
That would be pretty cool.
What?
If you just lock yourself and you become a pendulum.
You never did that? That was fun.
I guess I didn't have a childhood.
Okay. Well, there's plenty of swings around near, but there's nothing stopping you. Just, just go have some fun. Just go to the nearest park and go there at 3 a.m. and just silently swing for like 3 hours until daylight. Just, when the cops are called, just keep swinging. Just keep swinging. And wear a t-shirt saying just keep swinging. That says keep swinging. Anyway, don't do that. Anyway, or if you did, I don't know you. Anyway. Great. Oh, no, there's an audio recording of this crap. Anyway, editing. Anyway. Damped vibration. So what is damped vibration? Any idea? What does dampening mean? Damped means there is going to be energy loss from the system. Yeah, but you're right. It will decrease in amplitude.
So that.
Yes, and many times as engineers, we're trying to get systems that are very damped. We want to actually reduce the vibration as fast as possible. Now, in reality, all vibration, at least in terms of any real system, any kind of system you actually have is going to be damped vibration. In other words, there is always going to be energy lost. And really, so undamped is really an idealized model. We can sometimes approximate the behavior of certain systems as undamped if they have relatively low losses. But an undamped vibration, in undamped vibration, energy is not lost from the system.
So like those springs that they put like in the bottom of the support system of the bridge, that's kind of, would that be damped?
That would definitely be damped. If we have like a spring system for a bridge, or think about think about this. Do you want the springs for your car's suspension to be damped or undamped? You want them to be as damped as possible without just being a metal block, right? I mean, you want them to go into vibration so they can absorb some energy, but you need to be able to dissipate that energy as quickly as possible without, causing discomfort to people. Because imagine that. Imagine you went over a pothole and your car was vibrating for 5 minutes. That really wouldn't work very well, would it? I mean, because you're going to hit another pothole and then you're going to put more energy in the system and it would be a nightmare. So what you want it to do is, like in a, your car suspension, if you go over a pothole, you want the displacement to go something like this. You want it to go kind of like that. That would be a very damped system. If you have a system that is almost undamped, it would just be like that, barely, losing energy very, very slowly eventually. But even so, I could just draw it like even worse, I guess. Whatever.
So are your shocks like dampeners with dampeners?
Huh?
Are shocks essentially dampeners with dampeners?
Dampeners with dampeners.
Like they're damp.
Oh,
they're to dampen.
yes, that the shocks help. Yes, the whole system acts. I'm talking about the whole system, not just the springs, but yes, the whole system acts as dampening. Yes. Anyway, and this is primarily in the form of frictional energy. So, oftentimes as engineers, we are trying to design a system in order to reduce or isolate systems from vibrations, things like that. In fact, there are certain cases where this is absolutely critical. For example, things like an example that I'm aware of is electron microscopy. Something like an electron microscope. These are high-power electron microscopes. Certain ones of them can actually... We do have certain electron microscopes that are powerful enough to produce images of single atoms. Imagine the level of precision needed in a device like that. If you're going to build a device like that in a laboratory, you need... Laboratory? Well, okay. Pretentious much? Anyway, laboratory. In a laboratory, in a lab, you need to actually build your building with this in mind, or severely renovate your building with this in mind, because if you're dealing with very microscopic, atoms with precision here, your microscope will be vibrated substantially and vibrated out of alignment by the vibration of a truck passing by on the road outside the building. I mean, if you think about it, does that make sense? I mean, if you are, or even somebody in the hall walking past, slight vibration. I mean, does that make sense? As I walk across the hallway, walk across the floor here, it makes sense that every time I put my foot down, a little shock wave goes out through the building, throughout the entire building, and eventually through the whole earth. A small displacement of force, a small shock wave goes out and vibrates. If I walk across this room, I am actually moving every single person along the way. The power, yes. Anyway, I once did a calculation and realized at any given second I'm actually at any given moment I'm committing enough crimes in the state of Louisiana to be locked away for multiple life sentences. Did you realize that? Because apparently I once heard that the definition of assault in the state of Louisiana was to involuntarily apply a force to someone. It doesn't say anything about magnitude. So every time I'm walking or moving at all, or even breathing, I am adjusting my own gravitational field slightly. So applying a slight change in gravitational force to every single person in the state of Louisiana, which is talking millions of counts of assault in the state of Louisiana every second I'm alive. So yeah, I probably should say the state of Louisiana, but anyway. So anyway, that would be a circus to try, but anyway.
Turn yourself in before the fine.
Yeah, no, I'm not gonna, no. No, thank you.
These buildings, high rises that have the system in the upper floors, is that a dampener?
Yes, what you're talking about is a tuned mass damper, what they have in some high-rise buildings. They have a large weight on a series of springs or a series of hydraulic cylinders or something like that. And the idea is, in fact, let me just pull it up. Why not? I'll keep this. I'll probably go to Wikipedia, but that's okay. We don't need that. Tuned mass damper. Or harmonic absorber. Look at this. Yes, this is Taipei 101. I think it was surpassed by the Burj Khalifa as the world's tallest building, but it is still in existence. It's one of the top 2 or 3 tallest buildings in the world. And at the top of it, it has a large tuned mass damper. And this is just a large object hanging from cables and supported by springs and things like that, that it's tuned in such a way as to decrease the vibration of the building as a whole. See, the limit, we're actually at the point in high-rise design that our materials have gotten good enough that the limitation for high-rise design is no longer the limits on materials. We can build a tower quite high if we wish. The limit is actually, one of the biggest limitations we have is human physiology. See, structurally, there's nothing wrong with having a building, vibrating back and forth 10 feet, at the peak. That we can apply equations and say, hey, look, this is not going to overstress the concrete. This is not going to overstress the steel. Yes, it's moving 10 feet, but that's 10 feet over a 2,000-foot tall building. That's nothing. But if you're on the top floor working or living in a condo, or living in a condo or working in a office on the top floor, and your building and you are being accelerated back and forth slowly over a displacement of 10 feet, that is going to bother you. So the limitation is not just in the matter of, let's make sure this doesn't fall over. It's that people don't like inhabiting spaces like that. They terrify them, and rightfully so. I mean, I don't want to live in a building that's swaying back and forth in a light breeze. But even if you show them, even if you go up to someone and say, I am a very experienced structural engineer. I've been designing these buildings for 30 years. I'm an expert in structural dynamics and vibrational analysis. I am literally the best person in the world to do this sort of thing. I know what I'm talking about. They're still not going to want to live in your creepy, vibrating building, in your creepy, seasickness inducing building. So, and especially because if you're trying to, the other problem is that if you're trying to build the world's tallest building, you're probably going to be charging the world's highest rents, and people who can afford the world's highest rent don't want to live in a seasickness factory. So anyway, that's kind of the problem. So the limitations in high-rise design, it's not actually a matter of just keeping the thing from falling over. The challenge actually is to keep the thing from vibrating so much that people don't want to live and work in these spaces. But if you're talking something just like a radio antenna, well, then the radio antenna doesn't care, well, within limits. Anyway, so let us talk about simple harmonic motion first. This is going to be obviously the simplest state of vibration. And this is something I'm sure most of you have seen before. Okay? So let's talk about simple harmonic motion. So simple harmonic motion, this is undamped and free vibration. So this is going to be free, undamped vibration of objects and particles. It can be for an object or a particle. Free, undamped vibration. So here, I'm going to define a system. I'm going to work with the equations for a mass spring system, but the same thing would apply for any kind of system that was vibrating back and forth. Some similar equations would apply, but we're going to idealize this as a mass. We're going to look at an idealized system that's a mass spring system. So say we had an object with an initial position. This is the unstretched position here. So this is basically our x naught, or our origin point. Then you have, at any given instant, you have the object, the mass, at some distance from the equilibrium position. Again, this is if the thing is just resting. If I don't apply any energy to it, it's just hanging there under its own weight. It would be here. And when I stretch this weight down and release, it's going to bounce up and down, and it's going to have a certain peak amplitude, et cetera, and et cetera. So, and I'm going to call the position at any given time delta to refer to the, let's say, the displacement, okay? Okay, so I'm going to say this: if a particle is displaced xm, so xm meaning x max, from its equilibrium position, it will undergo simple harmonic motion from its equilibrium position and released with no velocity. With no velocity, it will undergo simple harmonic motion. It will undergo simple harmonic motion. Okay, so this is how you actually get simple harmonic motion. Then I want to label a few terms. So I want to first look at, I'm going to say the displacement at any given time is going to be delta. Maybe just be consistent with the book as the book has it, or as at least as Beer Vector Mechanics has it. I'll call it delta ST. And then then at the maximum point, it's going to have something like this. If I look at the maximum displacement, when this is at maximum displacement, if I draw a free body diagram of this, it is going to, where delta is the distance from equilibrium, the forces on here are going to be the weight, W, or mg, and the tension equal to the spring constant times delta ST, equal to the spring constant K times delta ST. Okay? And then, or actually that would be a true, well, at maximum that's what it would look like. But at any given, so this is, the tension is exactly equal to the weight when it's at the maximum displacement. However, at any case, what will apply is MA equals F equals W minus, so the sum of forces. MA is equal to the sum of forces equals W minus K times delta ST plus X equals negative KX. Okay. ST plus X here. Or negative KX. Or simply M X double dot plus KX is equal to 0. So this is more of our unifying equation. For simple harmonic motion, M X double dot plus Kx is equal to 0. And this is again for undamped motion. Then if we take this equation and solve for this, so again, we come back to M X double dot plus Kx is equal to 0. And if we solve for this here, we get that x, if we apply our differential equations, x equals C1 times the sine of the square root of K over mt, the square root of K over m times t, plus C2 times the cosine of that, square root of k over m times t. T is not in the square root there. Or we can also define the square root of k over m as the natural frequency. C1 sine, so we'll define these things again, sine of omega n t plus C2 times the cosine of omega n t. Okay, so again, omega n is going to be the natural angular frequency, or the natural circular frequency. And it is really a property of the object itself, or the system. Natural or circular frequency of the object. And it's, and notice it is a property of geometry and materials. It is a property of the object itself. Because notice, omega n is equal to the square root of k over m for a simple mass oscillator. So it's a property of geometry. That would be the k and the m. Well, both, I guess. Property of geometry and material. All right, so it's a property of the geometry and the material. And so that's a property of the system. And x is your periodic function. X is what is referred to as the periodic function. Periodic function. And C1 and C2 are determined by the initial conditions. C2 have to be found by solving for boundary conditions. So this is the general form of the equation, but to find C1 and C2, you need to apply boundary conditions. By applying boundary conditions. If you remember from your calculus. And this shouldn't surprise us, because if you remember, do you remember when you took simple integrals of polynomials or something like that? Remember back then when it's like looking back at, remember those days, those easy days, right? It's like Babby's first calculus, right? Good times, yes. What is the one mistake everyone always forgets on their first integral exam? Plus C, yes. You study your butt off and you're like, I know this stuff. You walk in there and you find you lose 2 points because you forgot the stupid plus C, right? That's always the stupid plus C. I'm not bitter about that. No, why do you ask? This is where these two constants are coming from. So notice if I want to get an x from an x double dot, the only way I'm going to be able to do that is by integrating twice. And so it should not surprise us that we have two different constants. We're going to have to integrate twice, so there's no reason we shouldn't have two different constants. And so again, C1 and C2 are found by the initial lower boundary conditions. So C1 and C2, again, we could say again that's x equals C1 times the sine of omega nt plus C2 times the cosine of omega nt. And also at any given point, we could say the velocity is equal to x dot, which is equal to C1 omega n, C1 omega n times the cosine of omega nt, omega nt minus C2 omega n, C2 omega n times the sine of omega nt. Where in this case, if you actually solve the boundary conditions based on the initial positions of the body and things like that, in our case, the way we've labeled things, I would say that C2 is equal to x naught and C1 is equal to v naught divided by omega naught. But it will vary based on what system you're considering. Okay? So, what if I wanted to plot the motion of the object? What if I wanted to plot the motion of an object? Well, we could plot it in terms of a circle, or we could plot it in terms of an angle, or in terms of a sine function, that kind of thing. Some other things, if I want to describe the motion of a body, or motion of an object in terms of this here, if I describe the motion of a simple harmonic oscillator, it's going to be a pure periodic function, a pure sine curve. It won't be decaying or anything like that, because again, it is going to be not losing energy. So I plot this out. It may look something like this. It's not going to be centered exactly at the x-axis, and that's or the y-axis, and that's okay. I should probably do that in black. So it might look something like this. Okay, so we would have our, here, let me label a few dimensions on here. Well, I would have a negative xm and a positive xm. Those would be the amplitudes. So the lowest value would be negative xm, and the maximum would be positive xm. So positive x sub m, and down here would be negative x sub m. And then, let's see, t would be the initial time or something like that. We'd have a little bit of an offset. Where, and then tau, let me just use maybe a tau here, because that's what our book uses, or at least the beer vector mechanics book does. Tn here, or tau. So tau would be our period, which is equal to, is the period, not to be confused with angular period or angular frequency, and this is just equal to 2 pi divided by omega n. All right. Then at any given instant, we could pick some given instant, and at any given instant we would have both an x, a displacement, and a time. So all this is doing is describing the displacement of this object versus time. And some equations to use that we'll need to be aware of and apply at various points. The x position at any given time would be something like x sub m times the sine of omega n t plus phi, omega n times t plus phi, where phi is our phase angle. That is the shift left or right needed to make this thing balance out, and that would be based off of a boundary condition. Xm, another way to find it would be to say that it is equal to x of the square root. Another formula for this, xm is equal to the square root of v naught divided by omega naught squared plus x naught squared plus x naught squared, and again that's the amplitude. And another formula for the phase angle. So phi is the phase angle. And if you don't feel like running through boundary conditions, one expression for it is that phi is equal to the inverse tangent of v naught divided by x naught omega naught divided by v naught divided by x naught omega naught. And then, of course, omega Fn, which you already discussed, is 1 over the natural period, where tau n is the natural period, or just the period. Let me label this maybe Tn here. And 1 divided by tau n, or omega naught divided by 2 pi, is the natural frequency. Natural frequency. Okay. And so that's describing displacement. So that is really, I might title this displacement time curves. Or equations. displacement time curves. I could also, again, for simple harmonic motion, but I could also describe velocity time curves and acceleration time curves. And acceleration time. We could define them in the same ways. Okay, and so if we start with x, we could simply differentiate these with respect to time. If I say x is equal to xm times the sine of omega naught t plus phi, well, v then would be equal to x dot, which equals, if we run through the derivative, xm times omega naught times the cosine of omega naught t plus phi. And then, or this is equal to, another way, we could shift this and say that it is equal to xm omega naught, because we can shift between sine and cosine by adding pi over 2, so we could if we wished. Omega naught times the sine of omega naught t plus phi plus pi over 2, or a is equal to x double dot equals negative xm omega naught squared times the sine of omega naught t plus phi plus phi, or this equals xm. If I want to turn this back into a, if I want to shift this to a positive value, I can add pi to it and it'll be the same. xm omega naught squared times the sine of omega naught t plus phi plus pi. Just a shift in phase angle. If we want, could make these positive instead of negative. All right, and maybe I can work through an example of this, of how we would work with something like this. Okay, so examples of this. Example, a simple pendulum. All right, so if I have a pendulum, and I'll look at an idealized pendulum that is a massless cord and a point mass at the end. So we're going to have an idealized pendulum with a mass of m and a length of L and an angle of theta. An angle of theta here. And I know the sum of forces. I could say, for example, the sum of forces in the tangential direction is equal to m times the acceleration in the tangential direction. And then I also know, if I do a free body diagram of this at any given time, well, I'm going to have the tension. I'm going to have two forces on here, the tension, and I will have the weight pulling down. And this will be at a certain theta. And this is going to be equivalent to a certain inertial diagram or kinetic diagram. That is like such. That is like this. I would draw this as I would need to have some sort of tangential acceleration. Sorry. Let's say a normal here. So MAN, or centripetal acceleration, and MAT, which would be the tangential acceleration. So this would be slowing the thing down in its rotation, and this would be causing it to rotate around. But if I do a summation in the tangential direction, so in this t direction here, and these are, of course, at a right angle, what would I get? Well, I know that this would be negative w times the sine of theta, negative w times the sine of theta. In other words, if I do it in the tangential direction, I know the tension will not produce any tangential force, so I can just look at the negative component of w in the tangential direction. And then is times the sine of theta is equal to ml theta double dot. ml theta double dot, that's going to be the acceleration. In other words, it is the angular acceleration transformed into a rotational, I start with the angular acceleration, then transform it into a arc acceleration by multiplying by the radius, then I transform it into a force by multiplying by the mass. That's how that equation comes about. Or I could reduce this to theta double dot plus g over L, if I replace W with g over M, or if I just cancel out the, if I replace W with M times G and then cancel out the M, I can get this, G over L sine theta equals 0. So that's interesting. Look here. Look what we note. The behavior of the pendulum will not depend on its mass. In other words, the period of the pendulum will depend only on the acceleration due to gravity and the length L. That's always a question I love to put in exams. Things like, how do you measure the acceleration of gravity in the planet you're on in an enclosed room? Anyway, that's something fun you could do. For example, I always thought that was cool. You could measure the acceleration due to gravity using only a pendulum and a stopwatch. Or you could measure the mass of a planet indirectly with that if you had the gravitational well, maybe not the gravitational. The mass would be a problem, but anyway, maybe. Okay. I'm thinking about it. Yeah. Anyway, okay. So I could, but then for small angles. Well, what is special about small angles? Remember the small angle assumption that when angles are small, sine of theta is approximately equal to theta. Remember that? Sine of theta is approximately equal to theta. I'm sure you've seen that at some point. So, I hope you've seen that at some point. And so theta double dot would be equal to G over L times theta equals 0. Or sorry, theta plus G over L. G over L times theta is equal to 0. And then, although then I could say theta is equal to theta m, the maximum theta displacement, times the sine of omega n, so applying the equations from earlier, omega n t plus phi, which if I were then to put in some boundary conditions, I would get tau n, the natural period, is equal to 2 pi over omega n, or equal to 2 pi, this is probably what we saw in high school, 2 pi times the square root of L over G, length over the acceleration due to gravity. So the frequency of a pendulum, or the period of a pendulum, is 2 pi divided by the square root of L over G. So that's an approximate solution. But then if you were to do an exact solution, this would require numeric integration. It would become more complicated. If you started with theta double dot plus G over L times the sine of theta is equal to 0, well, if you solve this, you would get something like, you would have to do something like this, where tau n is equal to the 4 times the square root of L over G times the integral from 0 to pi over 2 over d phi times the square root of 1 minus sine squared times theta m over 2 times sine squared phi, which would be a bit of a nightmare, but you'd have to do this numerically. Anyway, so regardless, we will not have to do that on the exam. So that's good, I suppose. Okay. And there would be some examples we could look at going forward. Okay, so let's take a quick break. We'll come back and look at this in some more detail. Okay. All right, and thank you.